everyone! Welcome to part 4 of chapter 17. Today we are going to talk about ionic solids dissolving in aqueous solutions. So this will be solubility equilibria. So we've talked about ionic solids dissolving in water, and we've classified some of them as insoluble, right? We've been working on those net ionic equations, and sometimes we come out with insoluble compounds and sometimes we have soluble ones. But in reality, all ionic compounds dissolve in water to some degree, right? So these ones that we're classifying as insoluble, in reality, they do dissolve a little bit. Their solubility is just so low that we tend to classify them as insoluble, but they do in fact have some ions that remain in solution. So we can apply these concepts of equilibrium that we've been learning about to these salts that are dissolving, and we can come up with an equilibrium constant for this whole process, and then we can compare the relative solubilities of, quote unquote, insoluble compounds. Okay, so our solubility product, right, we're going to learn another K value. We've talked about Ka, Kw, Kb. Now we have Ksp, okay? So Ksp is called our solubility product. And the way it's always going to be written is we're going to have some solid on the left, and it's always going to dissolve into its ions, okay? Even if it's an insoluble compound, right? Now we're saying, okay, well, there's no more really insoluble compounds. Now they, are just compounds with very low solubility. So we're going to write our solid on the left and then the ions that it would break into on the right. And I know it looks a little bit confusing with this whole NM process, but essentially these subscripts here will become the coefficients out there, and then, just these are the charges just like normal, okay? And the way that we write the solubility product is we're always going to have our ions in brackets, and then these numbers in the front, right, these coefficients are going to become our superscripts, okay? So we're always going to say that we have the concentration of our ions raised to the power of their coefficients. Okay, and so when we multiply those together, we will get Ksp, or the solubility product. And so our example, I think, makes a little more sense. We have lead chloride, and lead chloride would be insoluble, but again, we're going to, say that now it just has a very low solubility. So it will dissociate into its ions. So we have lead 2+, and we have 2 chlorine ions because of this 2 here. Okay, and so then when we write the solubility product, we're going to have our ions being multiplied by each other, and then that 2 will now become the superscript here. So we're always going to raise them to the power of the coefficients. You'll notice this lead chloride here doesn't appear in our Ksp expression, and that's because it's a pure solid. So we're going to say that its concentration is constant, therefore we don't include it in our K expressions, right? All of the same rules still apply to this value of K, right? Just like we've learned about with all of our other ones. So don't include don't include solids in your equilibrium expression. Okay, so here's a bunch of solubility constants, and you'll notice they all tend to be very, very small. Right? Again, this is kind of like what we talked about with the weak acids, where they don't dissociate very much in water, right? Most of them kind of stay together as that, original molecule. Well, again, these are all going to be, again, quote unquote, insoluble compounds, right? So their solubility is really, really low. Most of it will stay as the solid, and very few ions will actually dissociate and, float around in water. So that's where we're seeing very low values for some of these Ksp expressions. All right, so in general, we talk about the solubility as the molar concentration of the ions raised to their stoichiometric powers. That's what we were just looking at, right? And that Ksp is the product of the equilibrium concentration of the ions, meaning we're going to multiply them together. When we talk about solubility is just the amount of solute that will dissolve in a given amount of solution at a particular temperature, right? And so that at a particular temperature part is important, because as you increase the temperature, typically, not always, but typically we will increase the solubility of our salts, right? We can usually dissolve more of our salt at a higher temperature. So all of these Ksp values are only going to be good at 25 degrees Celsius. If you were at a different temperature, you would have to look up a different Ksp value, okay? And so solubility, though, doesn't tell you moles or grams or, or what. Normally we are going to be calculating the molar solubility, and that will be moles of our solute per liter of a saturated solution. But sometimes you will be asked to calculate it in grams per liter, and that's really easy. You'll just convert your moles into grams using that molar mass, and on you go. Okay, let's go ahead and try some of these. So for the salt silver iodide at 25 degrees Celsius, we have our KSP value, and I want to know what is the molar solubility in water. So again, we're looking for moles, so it'll be moles per liter. Okay, so we have our expression here. So silver iodide is our solid, and we are going to break it into its ions. Because they are both on a 1-to-1 ratio here, we don't have any coefficients that are happening. Okay, this is an equilibrium problem, so naturally we need an ice table. Okay, you'll notice I've put the letters ICE directly under the solid. You can do that, or you can put it off to the left and just kind of cross out under the solid like we do for pure liquids like water. But the reason that I have it there is just we're not going to use that column. The only thing that we care about are going to be these aqueous ions. So at the beginning, we are going to assume that all of our solid is just our solid. None of it has dissociated into ions yet. So we're going to put zeros for our ions. Okay, well then normally if you're thinking about our ice tables, we would then say, okay, well some of our solid is going to dissolve. So those are going to be plus X. Well, just to make it, more difficult or confusing or whatever, here for solubility, we use S. Just S for solubility to show that this is something dissolving rather than something reacting. Okay, so that's our difference here. And then if we add them straight down, 0 plus S will give us S. And then we can go ahead and put that in our KSP value, KSP expression. So our KSP is going to be our silver times our iodide. And again, we don't have any coefficients, so we're not going to have any superscripts. So then we can go ahead and fill in our equilibrium values. So they are both S here. So I'm going to fill in S for both of those. So then we can, our KSP value, we can fill that in for KSP. And then I put my S's together and got S squared. And then we can take the square root and we will get our value for S. And our value for S is the molar solubility of silver iodide. Okay, so this is very similar to problems we've done before, and actually in a lot of ways I think it is easier and more straightforward. Let's go ahead and try another one. So you'll notice in lead chloride, right, we don't have that 1-to-1 ratio that we did in the last problem. Now, for every 1 lead, we're dissociating into 2 chlorides. So we go about this the same way though. All right, so now we've made our ice table. So again, we are not starting with either one of our ions. So we're just gonna fill in 0 there. But just like we would if we were doing equilibrium problems, right, we're always going to use our coefficients in front of our S values, just like we would in front of our X values. So lead still gets the plus S, but now chlorine gets the plus 2S because of that 2 there. Okay, so we're going to carry that coefficient down. And then we add them together, we'll get S and 2S. So now when we fill them into our KSP expression, right, we have our lead times our chloride raised to the power of its coefficient. So we've got to square it because of this 2 out front. So I like to remember this as you're going to use this 2 twice. You're going to use it here and you're going to use it here. Okay, so just make sure that you are using that 2 in front of the S as well as using it in your KSP expression to square the concentration of the chloride. And so what ends up happening is you get, your S for the lead, but then you get 2S squared. So again, you'll see that it's showing up twice, right? The 2 is showing up in front of that S as well as squaring the concentration. So when we go ahead and work all this out, we get our KSP value from up here is equal to 4S cubed, right? Because this will be S times 4S squared. So we're getting 4S cubed. So then if we divide both sides by 4 and then we take the cube root, we can get S is equal to 1.6 times 10 to the minus 2 molar. That would be our molar solubility of lead chloride. And it's actually pretty soluble. All right. I want you guys to go ahead and practice this to get a little bit, to get a little practice before we move forward, because we're going to make it a little bit more difficult now. So go ahead, pause here, work these out, and then I'm going to work through the answers with you when you're ready. Okay, let's go ahead and work these out. So the first one, we're going to calculate the molar solubility of silver chloride in water and then of silver phosphate in water. So silver chloride is very similar to the very first problem that we did. So we've got our ice table here. Silver chloride, we're not going to start with any of them. Both of them will have a plus S because there's no coefficients here, right? So we're not needing to carry that coefficient down. So when we add them together, we're just getting S. And then we'll fill that into our KSP expression, right? So we'll multiply our ions together. And when we fill those in from our E values, those are both just S, which gives us S squared. And then we can take the square root of our KSP, and we can get 1.3 times 10 to the minus 5, or the molar solubility of silver chloride. This problem, really straightforward, not a lot to it. The silver phosphate one, though, is a little bit more exciting because now they are not on a 1-to-1 ratio. Now we have 3 silvers for every phosphate ion. So when we make our ice table here, we're not starting with any of either one of them, but for our C value, right, remember that you need to take this 3 down with you. So we're going to get 3S for silver and just S for phosphate. So when we fill this in for our KSP, make sure, again, that you are using this 3 twice, right? We used it once here, and we are going to use it to cube the concentration of silver, right? We're always, when we write these KSP values, we're always writing our ions to the power of their coefficients. Okay, so then when we fill this in, we've got 3S cubed times S, which is, 27S cubed times S, which gets us 27S to the 4th. So if we divide both sides by 27, and then we take the 4th root, then we can get our S value, which is 1.6 times 10 to the minus 5 molar, which is the molar solubility of silver phosphate. Okay, so this problem is very different than the last one because we have that coefficient there, because these ions are not reacting on a 1-to-1 ratio. Okay, so our molar solubility, as you've seen, is related to our KSP, right? We multiply the molar solubilities together, right? That's our S value, and we can get our KSP. But we can't always compare the solubilities of these compounds by comparing their KSP values because they're not always reacting in the same ratio, right? When we had the silver chloride, that was a 1-to-1 ratio, but with the silver phosphate, we needed 3 silvers for every 1 phosphate. So we can't compare those KSP values to each other because they have different dissociation stoichiometry. They're not dissociating into equal numbers of pieces. So you can only compare the KSP values for things that break into the same number of pieces or break apart the same way. Like we could compare silver chloride versus silver iodide because they both have a 1-to-1 stoichiometry there. We could compare, magnesium hydroxide to like magnesium chloride, right? Because again, they have the same stoichiometry, but we can't compare these to each other because silver chloride breaks into 2 pieces, whereas magnesium hydroxide would break into 3. All right, let's go ahead and talk about some other things that can go on with solubility. So there's this thing called the common ion effect. And if we were just looking at, say, calcium fluoride dissolving in water, water doesn't have any of these ions in common with calcium fluoride. But say there was something else in the water. Say there was fluoride in the water, okay? If we have fluoride in the water, if we think about this in terms of Le Chatelier's principle, right? If we have fluoride, that is increasing our concentration of our fluoride here. And when we increase the concentration of the fluoride, that is going to shift our equilibrium to the left toward the formation of the solid. So if we have a common ion present, so if we have something in the water that is also in our solid. So it has to be, present in the water, right? Present in our aqueous solution and present in our solid. It has to be one of the pieces of our solid. So if both of those things are true, then our solubility is going to be decreased when the common ion is added because an increase of the concentration of that ion is shifting the equilibrium back toward the formation of the solid. Okay, so in this instance, we added fluoride from NaF. Remember that, sodium fluoride is very soluble. Anything with sodium is going to be soluble. So when we add sodium fluoride, we have a bunch of free fluoride floating around. So it's increasing the concentration of our fluoride, shifting it toward the formation of our solid. Our sodium is not affecting this reaction in any way because there's no sodium present in the reaction. Had we added calcium fluoride, right, then that would make our problem even trickier. But here, the only thing that sodium fluoride and calcium fluoride have in common is that fluoride. Okay, so as we increase the concentration of our fluoride, calcium fluoride is being formed, and we are causing further precipitation. Okay. So let's go ahead and look at how we would do this mathematically. Okay, so this says for the salt silver iodide at 25 degrees Celsius, we have a KSP value, and I want to know what is the molar solubility in 0.05 molar sodium iodide. Okay, so this is going to be done exactly the same way, except for one step. Right now, we are not starting with zeros at the beginning because we already have stuff in our solution. Okay, so when we make our ice table here, if we think about sodium iodide, if we think about our sodium iodide is going to break apart into Na plus and I minus. Okay, so when we put our 0.050 molar sodium iodides in water, right, we are getting 0.05 molar of each of these ions because it's breaking apart. So now we are starting with that as our concentration of our iodide. Okay, we still don't have any silver because we haven't added anything that has silver, but we do have iodide here. So now we're going to go through and we're still going to put plus S and we're going to add them straight down, and it's going to be 0.050 plus S. Okay, this is going to be very much the same as when we were doing all of those weak acid and weak base equilibriums, right? Where we can assume that the change is negligible. Because if you look at this KSP value is very, very, very small. Silver iodide is not very soluble. Okay, so this plus S here is going to be negligible, like way negligible. So we're just going to end up getting rid of that, just kind of like we did previously in the weak acid and weak bases. Okay, so when we have our silver iodide, we would take our S and our 0.05 plus S, and then we'll get rid of the plus S piece. Okay, again, we're going to say that our change in concentration is negligible because if we look at that KSP value, right, that's telling us it's really not going to dissociate anymore. So then we can go about solving it. Okay, and this makes it pretty straightforward. Just going to divide both sides by 0.050, and then we'll get our S value. So if we look, our S value, right, our molar solubility here is really low. Okay, really, really low. If we look at what it was in water, 1.2 times 10 to the minus 8 molar, right? It's still not very soluble, but by adding our sodium iodide, right, that common ion, we have decreased the solubility even further. We've made it even less soluble. Because if you think about it, right, there's already a bunch of iodide floating around in there. So if we have a bunch of iodide floating around in there already, very little of that silver iodide will be able to dissociate, right, and dissolve because it's already got a ton of iodide pushing the equilibrium back towards the formation of our silver iodide. Okay, so our solubility is always going to be lower when we have a common ion present. So here it is graphically. So this is just showing you that as you increase the concentration of our common ion, we are rapidly decreasing our molar solubility. Okay, even if something had decent solubility in pure water, as you increase the concentration of your common ion, you're going to get a very, very, very rapid decrease in solubility. All right, I want you to go ahead and try these problems. So we have two different ones. We're looking at the solubility of silver chloride in calcium chloride and then in calcium nitrate. So go ahead and pause here, try and work these out, come back when you're ready. All right, let's go ahead and work through these. So we're looking at the solubility of silver chloride in calcium chloride. Okay, so they already have a common ion here. We see the chloride and we've got chloride, so this is a common ion problem. Okay, so we know that we are going to start with some amount of chloride at the beginning. We're not going to start with any silver because there's no silver present in our calcium chloride, but we will start with chloride. Now, if we look, we are starting with calcium chloride, which is CaCl2. And if we look at the way that it breaks, right, calcium chloride is going to break apart into Ca2 plus and 2 Cl minus. So for every 1 calcium chloride we are putting into our reaction, we're actually getting 2 chloride ions floating around. And what we care about is the chloride alone, not the calcium chloride. So when we take our 4.00 times 10 to the minus third molar calcium chloride, again, for every 1 calcium chloride, we're getting 2 chlorides. So we're actually going to end up doubling this molarity for the chloride because of the way that it dissociates in water. So then when you go ahead and do your ice table, right, our silver chloride, we've got our ice table there, and so that is going to be the molarity that we're starting with here. Okay, again, that is because our calcium chloride breaks apart into 2 chloride ions. Then we can go through, our plus S, and we've got, we're adding straight down, and we can fill that into our KSP expression. So again, because our KSP value is very, very small, we can say that, our change in our concentration is going to be negligible, so we can go ahead and get rid of that plus S there. So then we can go about solving for S, which is divide both sides by 8.00 times 10 to the minus 3. And we will get the molar solubility of silver chloride in our calcium chloride solution. Again, it's not going to be very soluble because we have that common ion present, which is shifting the equilibrium back toward the formation of the solid. All right, the next one, I like this problem. It says calculate the solubility of silver chloride in calcium nitrate. And so you're probably working through this problem and you're like, I don't know what to do. Or you may have caught it. There is no common ion here, right? Nothing in calcium nitrate is showing up in silver chloride. This is not a common ion problem. We are going to treat this exactly like it dissolved in water, because it's the same thing. We don't care about the calcium. We don't care about the nitrate. We only care about things that show up in the silver chloride. So we calculate this just the same as we would in water, where we're starting with neither of our ions. We have plus S of both, and we're just going to go through and solve. And we've actually already solved this problem. Okay, so our solubility in our calcium nitrate is going to be exactly the same as our solubility in water. Okay, the other thing that can affect our solubility is pH, right? So we just talked about our common ion. Now we're going to talk about pH. Again, this has to do with Le Chatelier's principle. So if we're looking at our calcium fluoride again, it may not be obvious right away that, this is going to be pH dependent, but let's think about this. So if we go with me, the last one, we increased our concentration of our fluoride. Now we're going to decrease our concentration of our fluoride. So if we were to decrease our concentration of our fluoride, that would shift our equilibrium toward the formation of more fluoride, right? Which means that more of our solid would dissolve into our ions to produce more free fluoride. And the way that we would remove this fluoride is by adding acid. If we add a strong acid, maybe hydrochloric acid or nitric acid, something that's going to completely dissociate and have, H plus floating around by itself. If we put a bunch of H plus in there, it's going to react with our F minus and produce HF. And so this actually causes our fluoride to be removed from solution because it's being removed as hydrofluoric acid. Our hydrofluoric acid has nothing to do with our solid, right? Except for the fact that it is decreasing the concentration of our fluoride. So as we add H+, that's going to remove our fluoride from solution. So as we decrease our fluoride concentration, we are shifting our equilibrium to the right, which causes more solid to dissolve. So as pH decreases, right, that's increasing our concentration of hydrogen, then our solubility will increase. Okay, and this is going to work for any basic anion. So anything that you see that is the conjugate base of a weak acid, then we can do this with. So you just need to be really familiar with what might be, a conjugate base of a weak acid. Let's, say you saw acetate, right? If you saw acetate in there and you added a bunch of H+, right, then we would be making acetic acid, which we would recognize as a weak acid. So this is another one where if, say you were trying to say you had something you were trying to dissolve with acetate. It's kind of a bad example because most things with acetate are really soluble anyhow. But if you saw something with acetate, right, same kind of thing. If you increased our concentration of our hydrogen ion, that would remove our acetate from solution as acetic acid, and it would make it more soluble. Okay, and the effect of pH on solubility is really, really dramatic. Okay, you can make a big impact on the solubility of something by changing the pH. Okay, so this also works for insoluble hydroxides. Okay, so like magnesium hydroxide, and this one I think it's really easy to see. If you added some acid, right, you added a bunch of H+, that is going to react with that OH-, right, and it's going to make water. Okay, so as we add our H+, then it's going to remove our hydroxide from our solution as water. And as we remove our hydroxide, that means our equilibrium is going to shift to produce more hydroxides, right? Which causes more of our solid to dissolve. Okay, the opposite though is also true. Let's say we added, we had a really basic solution. Well, if we had a really basic solution, then that would increase the concentration of our hydroxide, which would cause less of it to dissolve. Okay, so these hydroxides here are going to be really insoluble in basic solutions, but very, very soluble in acidic solutions. Okay, so again, you're just going to need to see, what's attached to it. Is that going to act as an acid or a base? What's this ion doing over here? So if we have something like calcium carbonate, so carbonate is going to be the conjugate base of a weak acid, right? If we think about carbonic acid or bicarbonate, bicarbonate is actually amphoteric. It can act as both an acid and a base. But either way, right, this carbonate ion can add a hydrogen onto it and form our, a weak acid. Okay, so carbonate is going to be one of them that is, very affected by pH. So the lower the pH, if the lower the pH, the more the hydrogen ions that are in there, right, that will remove that carbonate from solution and it will shift, right, we remove it, it will shift toward dissolving more of that solid. All right, let's go ahead and think about this. So I have two questions for you. This first one says, how does the solubility of silver chloride in water compare to the silver chloride in an acidic solution? And in this case, I added nitric acid to my solution. And I want you to explain it. So go ahead, pause here. I want you to think about this. Silver chloride in water versus silver chloride in an acidic solution. All right, here's the answer. Solubility is going to be exactly the same. And the reason that it's the same is because if we think about, silver chloride dissolving in water. Silver chloride in water will make Ag+ and Cl-, okay? Neither one of those are going to have any acidic or basic properties, okay? Our silver is just a metal ion, so we're not going to worry about that. And the chloride, if we think about what the chloride is the conjugate base of, well, the chloride would be the conjugate base of hydrochloric acid. Hydrochloric acid is a strong acid, so that doesn't play by the rules that we were just talking about. If we had hydrochloric acid, then it would just dissociate back into H+ and Cl-. It's not going to have any acidic or basic properties. So silver doesn't have any acidic or basic properties. Chloride doesn't have any acidic or basic properties. So it's not going to be affected by the pH of the solution. So it doesn't matter if it's, acidic or not. It's going to dissolve just the same. All right, here's another one. How does the solubility of silver phosphate in water compare to that of silver phosphate in an acidic solution? So same question, just now we're looking at silver phosphate. So go ahead, pause, think about that one. Okay, so let's go ahead and think about this. So silver phosphate in water, right, we could go ahead and calculate that. But silver phosphate in acidic solution, that's really what we want to know. Again, the acid is not going to affect the silver, that's just a metal, but the phosphate though, the phosphate can add a hydrogen and make HPO4 2-, right? Again, remember, this is all coming from phosphoric acid, which is a weak acid. So the fact that this is, a conjugate base of this weak acid, we could go all the way back to phosphoric acid, right? But this is a weak acid as well. Since it can make a weak acid, right? This is a conjugate base of a weak acid. It will be affected by pH. So the silver phosphate is more soluble in an acidic solution because the hydrogen can go and react with this phosphate and make this ion. And as we do that, then that means the phosphate is being removed from solution as this. So as we are removing phosphate, that means that more of that solid can dissociate, and so we are getting more and more of it dissolving, which means it has a greater solubility. Okay, so this is how pH is affecting these. You just need to look and see, is this anion, it's typically going to be the anion, but is this anion going to be affected by the presence of hydrogen? Can it make a weak acid? And if your answer is yes, then it can be affected by the pH. All right, and that is the end of our lecture on KSP. So we've talked about the fact that insoluble ionic compounds are not really insoluble. In fact, they're just, slightly soluble, really. I mean, like really, really, really slightly, but they are soluble a little bit. And we can calculate that using the KSP value. We've looked at how to do that. We've also looked at how to calculate the KSP, or the molar solubility, in a solution with a common ion. And we've looked at how to take into account the effect of pH on these KSP expressions. Okay, so we've covered a lot of ground today about dissolving ionic compounds in aqueous solutions. Make sure you're getting a lot of practice on these by completing the lecture worksheet problems. There's quite a few pages on them. We are going to use this whole process, or this idea of dissolving things in acidic solutions or with common ions. We are going to use that in the next couple lectures, and we are also going to use that when we get to qual. So make sure you are really understanding how these problems work, both conceptually and mathematically. If you're ever having trouble, please reach out, ask me lots of questions, and I am happy to answer them. Otherwise, keep working hard, and I will talk to you all next time.